Okay, so continuing on from my last video based around a SolidWorks model of this same question. This question is from Anderson's book, and I'm just going to explain some of the principles about where we take our different heights and our measurements from. So, as we said before, it's two cylindrical based ductings intersecting at 90 degrees. And the first thing we have to do is find the length of our development, and that is equal to the circumference of our ducting. So we do that by first drawing our center line here because we know it's a symmetrical shape. We then come along, take a distance from point 1 to 2, and then 2 to 3, and 3 to 4, and that's just a semicircle with equal radius to that of our ducting. And then we mark them points off all along our line that we've drawn, parallel to or at the same height of our ducting, and that'll give us 12 equal sections, and they're equal to the circumference of our ducting. And we then need to find points along the surface where the two ductings are intersecting, so we need to find the points along our line of intersection. And we can do that. I've got two examples here. So if I wanted to look for point 3, I can drop point 3 straight down in our end view where it hits our second ducting, so our line of intersection. I bring it horizontally across, and where that hits the line of intersection again, I bring that straight up to the top of our ducting, and I can take that height from there to there and mark it off at our third section over, and that'll give me point 3. And that'll be the point on our development, and that's true for all the points. Okay, so moving on from there, you're going to go on to a slightly more difficult question. This is from Anderson's book as well, and it's based around the development of a cylindrical based ducting intersecting with a prism based ducting or a square based ducting at 90 degrees and rotated at 45 degrees as well. So first off, you're asked to find the true shape of the hole that is cut into the ducting, into the cylinder based ducting, and to where the square based ducting is basically intersecting with it and joining to it. So what you have to do there is the same principles as what we used in our last question. So you're going to be coming down to our plan, because we can see our ducting as a circle. You can split that in half because you're only looking for the front section where the hole is going to be cut, and divide that into 6 equal parts, and that'll give you your radius or your circumference of half of your cylindrical based prism or cylindrical based ducting. Sorry. We then need to find our points, so we can take any one of them points, bring them horizontally till it hits our YY line up to 45 degrees, where it hits our line of intersection, bring it horizontally across straight to our developed surface, and then to find the distance between, or to find exactly where along that line our point is, we can use our compass. So say we're looking for point H, I'm going to just draw in a circle here from point H back to my center line of my square based ducting, and I'm just going to show you now that if that was on the center line, I would have drawn it slightly off, but if that was along our center line, it would be lining up with our point H and our point B because it's a symmetrical shape. So that's how we would go about finding our points for our hole that's cut into around our cylindrical based ducting. We then are asked to find half the true shape of the square based ducting. To do that, we need to know the length of two of the sides. So, but because it's our ducting is inclined at 45 degrees and turned at an angle, and we can't see the true length of any of them sides in any of the views we have, or elevation, end view, or plan. We'd have to either get an auxiliary or maybe use the rebatment method to find the true length of one of them. And the easiest method to use is the rebatment method, because we have this line here, our long diagonal between our 2 points, and we know that that's not going to change. So what we can do is we can come back up to our elevation, draw that line in again, rotate 1/2 of the square surface back down to the horizontal line, drop it down, and we get this shape here, which is our true shape. Now in the question they have the true shape over here. It's the same thing, they just moved it across, and they have it divided into 4 equal sections, and then them lines are then projected back horizontally, and we find our points using the same methods as before. So if I'm looking for point 2, I can draw a line from point 2 all the way across up my 45 degrees, and where it hits my line of intersection then, which is in here, I can bring it across to where it'll hit my line 2 coming down to along here, and project that back across again. And I know my line 2 is going to be along that line. So to find exactly where, we'll have already divided, we'll have used these divisions here from 1 to 2 and 2 to 3 and 3 to 4 to find our circumference. So these should be labeled, and that line there will be line 2. So if I was labeling that, I'd label that line 2, and see there's line 2, and that'll just make it easier for me to know that that line and my opposite line connecting is going to give me my point on my developed surface, or my half of my developed surface. So students should be really aware of true lengths, auxiliary views, and then the likes of rebatment, when it comes to intersecting of ductings. A student could make a cardboard model of this question. It's slightly more difficult to make, just because of all the angles and the curves of the developed piece. However, having a development of the first question could still be beneficial, and the students could still be able to look back on the key principles and see how they're folded down and how it works. So for the questions so far, for all of our questions, we've been drawn it that our developed surface is parallel. Our developed surface is parallel to the actual solid, and that's just to make it easier for us to draft it. We can bring lines across perpendicular to the edges, and that's something that we should do when we're drawing our auxiliary or our developed surface for something that's inclined either. So our developed surface is parallel to that of the actual solid or the ducting, and that just makes it easier for us to draft and easier for us to bring our heights back and across. Otherwise you have to reference off different points and draw it off again, and that'll just take more time. So that's just a handy tip for students to be aware of, to draw things parallel to the actual ducting. Thank you.